Welcome to This Explainer. Today, we're doing a complete under-the-hood breakdown of the architecture that is literally powering modern AI. If you've ever found yourself wondering how developers actually stop AI from just, making things up, or how they teach it all about private company data without spending millions of dollars doing it, well, you're in the exact right place. Let's just dive right into this. We're going to look at the concrete engineering steps that take these big, abstract AI concepts and turn them into highly accurate fact-checking machines.
So to really understand the solution here, we first have to fully understand the core problem. How do you actually stop an AI from hallucinating? Imagine a cutting-edge model, let's just say a hypothetical GPT-5, right? That finishes its massive multi-million-dollar training cycle on August 1st. Now, what happens if on August 31st, you ask it about a major news event that happened on August 15th? It has a massive blind spot because its training data is completely frozen in time on August 1st. It doesn't actually know the answer. But instead of just saying, hey, I don't know, it invents facts. It hallucinates, giving you this incredibly confident yet entirely fabricated answer.
Here is our blueprint for today. We're going to cover 1. The hallucination problem. 2. What is RAG? 3. The data ingestion pipeline. 4. The query retrieval pipeline. And 5. Simple versus enhanced RAG. Let's jump in. All right, part 1, the hallucination problem. Think about the psychology of a large language model for a second. Because it's frozen in time, it has these massive blind spots, especially when we're talking about proprietary data. Imagine a startup building an internal chatbot for its employees. Your highly specific HR leave policies or confidential finance rules, they aren't just sitting out there on the public internet. So if an employee asks the bot about bereavement leave, the model doesn't want to look foolish. It'll confidently invent a really convincing, generic answer based on public internet data that is completely wrong and honestly potentially dangerous for your specific company. For a long time, the assumed solution was fine-tuning. The logic was, if the model doesn't know your HR policy, just fine-tune it. But fine-tuning is an incredibly tedious, super expensive process. I mean, you are adjusting billions of parameters. And worse, company policies change constantly. You just can't afford to run an expensive fine-tuning cycle every single day just because somebody updated one single document. So the absolute crucial point here is that we need a cost-effective dynamic alternative. Instead of fundamentally altering the model's brain, what if we just handed it a reference library? Which brings us to part 2. What actually is RAG? RAG stands for Retrieval-Augmented Generation. Let's use a really simple analogy. Fine-tuning is kind of like forcing a student to memorize 1 million textbooks right before a closed book exam. RAG completely changes the rules of the game. It basically makes it an open book test. RAG is the process of optimizing a large language model's output by giving it access to a trusted external knowledge base right at the exact millisecond you ask a question. The model doesn't need to actually memorize your HR policy. It just needs to know how to retrieve it, read it, and hand you the right answer in real time. Get this, according to the developers building these systems, a staggering 90% of the AI use cases currently being worked on inside companies today are specifically related to RAG. It is the absolute gold standard for getting reliable, factual outputs from generative AI without completely breaking the bank on training costs. Let's ground this in reality and look at some real-world case studies. RAG is exactly what enables those internal startup chatbots to instantly quote complex internal finance policies. But let's look at this at a massive scale, the Perplexity AI's search engine. Perplexity is essentially just a giant RAG application. It fetches real-time web searches, uses them as an external knowledge base, and then synthesizes an incredibly accurate, summarized output without hallucinating. It's brilliant. Okay, part 3, the data ingestion pipeline. Before an AI can magically answer questions about your data, it actually has to digest it. This ingestion pipeline has 4 precise steps. First, we parse the data. This means using loaders to read unstructured files, a PDF, an HTML web page, or maybe a SQL database, and converting them into a highly structured document format that contains both the text and its metadata. Second, we chunk those documents. Third, we generate embeddings. And finally, we store those embeddings in a vector database. Let's break down why steps 2 and 3 are so critical here. So step 2 is chunking. You absolutely cannot just feed a 100-page PDF directly into an LLM. Every single model has a fixed context limit, basically a maximum number of words it can process at any one time. To beat this, we use tools like a recursive character text splitter. This takes a massive document and mathematically chops it up into smaller, manageable chunks, let's say 1,000 characters each, while making sure to leave a little bit of overlap so we don't accidentally slice a crucial sentence right in half. Once we have our text broken into these bite-sized chunks, we hit step 3, Embeddings. Look, AI models don't actually read words the way you and I do. They read numbers. We use open-source embedding models, like the All-Mini LM L6v2, to process these chunks. This specific model takes our plain text and generates embeddings, converting the text into a highly precise 384-dimensional numerical vector. By converting text into this crazy 384-dimensional geometry, the AI can mathematically calculate the actual meaning and context behind human words. And that brings us to the final step of the ingestion phase. We need a place to put all of these vectors. We use a vector database. Specialized databases like Phase or ChromaDB essentially act as the new brain for your AI system. Your proprietary data now lives securely inside this database, stored purely as mathematical vectors. And because everything is entirely numerical, this database allows us to perform lightning-fast similarity searches later on. Moving on to part 4, the query retrieval pipeline. So, here is the 5-step retrieval journey. Step 1, the user asks a query, something like, "What is our company leave policy?" Step 2, we run that exact query through the same embedding model, turning the question itself into a 384-dimensional vector. Step 3, we take that vector question over to our vector DB and run a cosine similarity search to find the text chunks that mathematically match our query the closest. Step 4, we retrieve those matching chunks, which is our context, and send them alongside our prompt straight to the LLM. Finally, step 5, the LLM generates our highly accurate output. The most crucial point in all of this is step 4, the augmentation phase. This is the magic moment where we completely shut down the model's urge to hallucinate. We don't just blindly hand the context over to the LLM. We give it a very strict set of instructions via a prompt. We literally tell the model, "You are a helpful assistant. Use only the following retrieved context to answer the user's question. If the answer is not in the context, say you do not know." By strictly merging the exact data with these rigid instructions, the model is forced to stick to the facts. And finally, part 5, simple versus enhanced RAG. When we look at the different types of RAG, there is a massive difference between a simple pipeline and an enhanced pipeline. Simple RAG gives you a basic answer based on the context, sure, but it really demands blind trust from the user. Enhanced RAG, on the other hand, is built for the real world. It is designed for surgically precise output. It provides hard source citations, so instead of blind trust, it gives you exact page numbers so you can actually verify the facts yourself. And instead of zero accuracy metrics, it utilizes math to give you confidence scores, proving exactly how strong the match actually is. And this illustrates exactly why parsing the data in that very first step was so important. Enhanced RAG relies heavily on metadata. Because we parse the documents properly up front, our pipeline retains the source file name, it logs the total pages, it tracks those similarity distance scores, and it can even surface a preview of the first 300 characters of the source document directly in the user interface. When you're doing really rigorous tasks like reading complex medical research papers or analyzing huge legal contracts, having hard citations pointing to an exact page number isn't just a nice feature, it is completely indispensable. For all the developers and tech teams out there tuning in, the ultimate goal is moving from these abstract concepts to modular, reusable code architectures. The industry standard right now involves breaking these steps out into modular Python scripts. So you have a dedicated data loader script, an isolated embedding manager, and a standalone vector store component. By designing the whole system in a modular way, your RAG pipeline becomes incredibly scalable. It allows you to swap out PDF loaders for SQL loaders or seamlessly upgrade to a more powerful LLM in the future without having to completely rewrite your entire codebase. Well, we've covered the complete journey today, from solving hallucinations to parsing and chunking data, right through to retrieving vectors and forcing LLMs to actually cite their sources. But technology never stops moving. Once you master the traditional RAG pipeline we just broke down, a whole new horizon opens up. Think about it. What happens when your retrieval system doesn't just read documents, but can actually trigger web searches, interact with external APIs, and make complex, multi-step decisions totally on its own? So I'll leave you with this provocative thought. Are you ready to build agentic RAG? Thank you so much for joining this explainer, and keep learning.